Welcome to the deep dive. The sources you sent us this week. Wow. They don't just hint at the future of energy, they really lay out a blueprint for it.
They certainly do.
We're talking about infrastructure that's completely autonomous, incredibly resilient, and, well, it's engineered to be almost invisible.
Mm-hmm.
It's a huge shift from just, consuming electricity to truly owning and securing your own power grid, right down to the millisecond.
That really is the core insight here. We're looking at a technological convergence. It's a complete stack hardware, AI software, and some pretty groundbreaking chemistry. All of it is designed to make legacy infrastructure obsolete.
And across all these sources, from Forerunner to GridOS to NovaSpark, there are really two big motivations driving this, right?
Exactly. It's all about the pursuit of two things: extreme resilience and genuine long-duration autonomy.
And what a stack it is. I mean, we start with the commercial side, these independent power solutions. Then we get into the AI, the GridOS that's managing everything.
A central nervous system.
Right. And then it gets really technical. We dive into how you generate clean hydrogen power just from the moisture in the air with NovaSpark.
And then it goes even further.
Oh, yeah. We hit the really extreme applications, the military-grade stealth infrastructure, and this is the one that blew my mind, converting energy into binary data for global transport. That's all in the Pyramid Core docs.
It stands out because energy is no longer just a physical commodity. It's fully merged with computing and, data security.
So, okay, let's unpack this. Our mission for this deep dive is to understand how all these different technologies converge to create these power systems that are self-sufficient, super secure, and can even move energy digitally.
Let's do it.
All right, let's start at that foundational layer. The commercial drive for independence you see in the Forerunner sources. The goal is capturing the sun, owning your grid. What's the biggest technical leap here compared to the usual solar and lithium-ion systems we see everywhere?
The critical differentiation is the storage chemistry and the sheer density it offers. I mean, yes, these solutions do use established batteries like lithium iron phosphate Life Pro 4 for some things.
Okay.
But the real leap forward is their proprietary solid-state battery architecture.
Solid state. That's been the holy grail in the car world for years.
Mm-hmm.
Why is it so important for grid infrastructure specifically?
It's all about density and safety. Solid state gives you much higher energy density in a smaller footprint, and that's crucial when you're trying to provide dispatchable, baseload power 24/7.
So when the sun goes down, you're not just out of luck.
Not at all. This architecture delivers reliable, high-power flow for hours. It ensures the grid doesn't skip a beat. It turns solar power from something intermittent into a guaranteed continuous supply.
I see. Okay, so if the technology is the engine, the financial model seems to be the fuel for adoption. The sources suggest the big aha moment for enterprise customers is how this changes their accounting.
It really is.
We're talking about taking operational expenses, OPEX, like their monthly utility bill, and turning it into a verifiable asset on the balance sheet.
Exactly. This isn't just energy conservation. It's a full-on infrastructure investment strategy. By installing these systems, a company is buying a depreciating asset that immediately offsets these highly volatile, unpredictable utility costs.
And the focus shifts to dealing with those massive peak demand charges.
Absolutely. Features like peak shaving and automated demand response are essential for heavy industrial loads. The system just proactively draws on stored power during the most expensive times of day.
Yeah.
It minimizes those penalty fees and delivers a really quantifiable return.
And they're deploying these on assets they already own but weren't really using for revenue, like roof space or parking lots.
Transforming parking lots into revenue-generating assets with these specialized solar canopies, yeah. They're just maximizing the potential of their existing real estate.
And getting access to the money to do it seems to be a key part of the strategy. The sources mention things like the instant tax credit, the ITC, and zero-down PPA financing.
Which is crucial for rapid deployment.
Okay, so for you listening, break that down. What does a zero-down PPA mean in real terms for a business?
It just dramatically lowers the barrier to entry. It means the company can install a huge multi-megawatt system, get energy independence instantly, and start saving money on their bills, often without spending any capital up front,
So they just buy the power from their own new system.
at a predictable, lower fixed rate.
Yeah.
It takes the financial risk off the table and really accelerates that transition away from the vulnerable grid to owning your own resilient infrastructure.
Okay, so you have all this advanced hardware, solid-state batteries, solar arrays, even hydrogen generators. You need a brain to coordinate it all.
And that's where the software layer comes in. If the hardware is the muscle, then the key to truly autonomous never-fail power is GridOS. It's the central nervous system coordinating generation, storage, and consumption.
And the speed of that coordination, I mean, that's what really stands out. GridOS operates with, what, millisecond precision?
It does.
So this predictive balancing is the AI sort of playing chess with the power flow.
That's actually a great way to put it.
Yeah.
It's not just reacting to a switch being flipped.
Yeah.
No. The AI is constantly forecasting. It's using historical data, weather patterns, real-time load behavior to predict when a major demand spike is about to happen.
Like a factory floor starting up a new line.
Exactly. And it adjusts the generation and storage output instantly to meet that predicted demand before the spike even registers on a conventional meter. That millisecond precision prevents brownouts and ensures maximum efficiency.
And this isn't all run from one central tower. It's decentralized. They call it peer-to-peer trading. How does that help a whole campus or community?
Well, when you have multiple connected nodes, say a factory and a data center on the same GridOS network, PDP trading allows automated energy markets to operate between them
So they're trading power with each other.
instantly. If node A is overgenerating solar and node B needs a little boost, the energy is traded internally. You're not relying on the distant main grid. It creates this mesh network of power that enhances the whole system's stability.
So if one node fails, the others just fill the gap automatically.
They do, which makes sense from a software perspective. But here's where the sources get into some really extreme engineering: resilience and security.
Right, military-grade capabilities. When they talk about physical hardening, what exactly are we talking about?
We're moving into critical infrastructure protection. The documents detail specific measures against these large-scale, low-probability, high-impact threats.
Things like EMPs.
Yes, physical safeguards like EMP-shielded enclosures, that's electromagnetic pulse shielding, and tamper-proof metering. They are building against physical intrusion and catastrophic events right into the hardware.
Wait, hold on. For the listener, why would a commercial energy solution need EMP shielding? That sounds like something out of a movie.
Because a high-altitude EMP event, whether it's from the sun or, intentional, can instantly fry unprotected electronics across hundreds of miles. It would cripple the conventional power grid.
So these systems are designed to just keep running.
They're designed to survive and continue operating even if the world outside is in a total blackout. It's the ultimate disaster recovery feature.
And on the cyber side, they have this dual strategy: air-gapped control loops and quantum-resistant encryption. Air-gapped means physically disconnected from the internet, right?
That's right. The most critical control loops, the ones that turn power on and off, are completely segregated from any external network. They run purely locally.
And the other data.
The non-critical transactional data like that peer-to-peer trading is protected by quantum-resistant encryption. It future-proofs the security against advanced computing threats. It's a zero-trust model.
And the feature that ties it all together is island mode, the ability to just instantly decouple from the main grid.
Instantly and seamlessly. The goal is never fail power, and this is how they achieve it.
But that only solves the problem for minutes or hours. For true independence, you need to store power for days or even weeks.
And that's the critical limitation of batteries, even solid-state ones, which is where we have to pivot to Novaspark
Yeah.
and their long-duration hydrogen solution.
Right. Clean power made from air plus electricity.
This closed-loop process is maybe the most elegant solution in the entire stack. It solves the logistics problem of remote power generation. It's self-sufficient. All it needs is electricity, which they already have from solar.
So let's walk through the 5 steps. Step 1, water from air. They're using atmospheric water extraction. What does that actually mean for deployment?
It means they've eliminated the single biggest constraint for traditional hydrogen production: the need for a stable, clean water source.
So you could put one of these in the middle of a desert?
You could deploy it virtually anywhere on Earth. It makes it a truly resilient, self-contained solution.
Okay, step 2, electrolysis. This is where they split that captured water, HERO, into hydrogen and oxygen.
And crucially, they're using solar or their stored electricity to do it. So zero carbon emissions at the point of use. You're producing pure, clean hydrogen feedstock right on site.
Then step 3 is the key for that long duration. The hydrogen is compressed and stored in these high-pressure tanks. Up to 700 bar. Why is that pressure so important?
700 bar is an extreme pressure. It's all about energy density. To store enough hydrogen to run a community for a week, you have to compress it that much. They use these special Type 5e composite vessels.
And that's what gives them days or weeks of autonomy.
That's it. It allows them to store energy for 24, 48, up to 168 hours of continuous operation.
Right.
That is long-duration autonomy.
Then step 4, the fuel cell converts it back to electricity. And step 5, the output is just clean electricity, pure water vapor, and maybe some recoverable heat.
A genuinely clean, closed loop. And it solves major problems. For an off-grid community, it completely replaces expensive, noisy, polluting diesel generators.
And for something like a data center, this must be a game changer. I mean, instead of a UPS that buys you minutes, you get clean backup power for hours or days.
Absolutely. But, handling high-pressure hydrogen demands intense safety protocols. And the sources are very clear on this.
They mention specific standards like NFPA2.
Right, NFPA2, SAC J2579. This isn't a DIY project. It's heavily engineered with multiple layers of safety.
What kind of features are we talking about?
Things like constant combustible gas detectors, forced ventilation systems to prevent any buildup, and specialized pressure relief devices. The engineering focus is all on containment and passive safety.
Okay, now we have to shift gears to the most extreme applications, the Pyramid Core and the Forerunner stack. This is where it all comes together. Energy, stealth, and autonomy.
And the scale is almost unbelievable. 1.2 gigawatts of solar generation capacity, deployable completely off-grid.
I mean, the Pyramid Core is designed to be the ultimate autonomous energy hub, but the wildest detail is at the very top of the structure, the Autonomous Drone Operations Hub.
Right. This isn't just about keeping the lights on. It's about extending operational reach.
The refueling capability, tell us about that.
The system can support the charging and automated redeployment of up to 50 UAVs, drones, in under 15 minutes.
No human intervention.
None. The stated goal is extending operational range by 10 times, enabling basically unlimited surveillance capability without needing vulnerable refueling convoys.
It's just hard to wrap my head around a power plant that massive being secure. But this is the big aha moment of the entire stack, the stealth profile.
Yes. It's engineered not just to be hardened, but to completely defeat aerial reconnaissance. The unique geometry makes the structure appear flat from above. The metrics are astounding.
Astounding is an understatement. The radar cross-section is less than 0.1 square meters from above.
Which is basically invisible to radar. It would look like a small bird or just ground clutter.
And it's not just radar.
No, they combine that with thermal management.
Yeah.
The IR signature is ambient matched. It doesn't emit a heat signature that infrared sensors can pick up.
So it's thermally invisible too.
And electromagnetically shielded to MIL STD 461G. They're ensuring this gigawatt power plant is perceived by any adversary as nothing more than flat, boring terrain.
That's incredible. But the ultimate pivot, the most complex idea we've encountered, is in the Forerunner stack's digital storage engine, this concept of energy data conversion.
This is where we move past physics and into pure computing theory applied to energy. It's a proprietary two-stage process. First, raw electricity is consumed by high-density compute hardware. We're talking up to 500 exaflops of power.
And that energy isn't creating heat or movement, it's just creating binary data.
Correct. The energy is encoded into complex data blocks. By converting physical power into digital information, the energy is now stored online, completely detached from its geography, and once it's data.
It can be transported globally as information via fiber optics?
Exactly.
So let me see if I have this right. A facility could generate massive solar power in, say, the Arizona desert, convert that energy into a huge data packet, send that data through a fiber cable into the Atlantic, and then at a hardened facility in Europe, convert that data back into usable grid-quality electricity.
That is the ultimate implication. It completely separates the generation source from the consumption point. It makes the energy supply globally movable and pretty much impervious to traditional physical threats, like pipeline sabotage or shipping blockades.
Energy becomes a liquid asset you can move at the speed of light.
That's a perfect way to describe it.
So if we connect all these themes back together, the very concept of an energy supply fundamentally changes, doesn't it?
It absolutely does. This stack of technologies moves energy from being a vulnerable, centralized physical asset like a power plant to a decentralized, intelligent, and potentially invisible utility.
Stored chemically as hydrogen.
Electrically in solid-state batteries.
Or even digitally as data. The vulnerability has been engineered out of the system.
It has.
So what does this entire deep dive mean for you, the person listening, who needs to understand the state of this technology?
I think it means recognizing that true energy independence today isn't about one piece of hardware. It requires integrating advanced physics like high-efficiency electrolysis and solid-state batteries, with autonomous digital control, with AI forecasting, with mesh networking.
And wrapping all of it in extreme resilience.
Exactly. From EMP shielding to zero-trust security and low observable design. It's a full-spectrum, integrated solution that really treats power as a secure, movable information packet.
Thank you for sharing these incredible sources
Yeah,
and diving deep into what is clearly the new standard for critical infrastructure.
my pleasure. And as you mull over these concepts this week, consider this final thought. If energy can be generated off-grid, converted into data, transported globally via fiber optics, and then converted back into physical power at a hardened, low observable site, what does that mean for global energy geopolitics? And where's the practical line between essential, secure energy infrastructure and critical, sovereign computing infrastructure? Raises an important question
Yeah.
for you to think about.